All right, so the last part of this chapter is kind of different. We're going to look at reaction arrow pushing, and let's kind of do a little bit of review. We've actually seen reaction arrow pushing before, where we show it with arrows. All right, what does the head of the arrow mean? And what I mean by that is, what does this indicate? It's the direction of what? The movement of atoms or electrons? Electrons, right. All right, so on one side of the arrow, we've got the electron destination. And to be more specific, we should say electron pair destination. And over here, we'd say this is our electron pair source. Does that make sense? So the main thing to remember, I'm going to clean this up a little, is anytime we show reaction arrows, we're always showing movement of electrons, not movement of atoms, right? All right, there's one other arrow system that you might encounter next term. Looks like this. What's the difference between the top one and the bottom one here? Sorry, this still looks messy. I'm going to fix this. There we go. Now it's clear. What's the difference between the top one and the bottom one? Well, if we look at this arrowhead up here versus this arrowhead down here, there's clearly a difference, right? It looks like a single-headed fishhook almost. When anytime you see an arrow that looks like this is a single electron. And then this will be the destination for one electron. So you might see this occasionally. We really won't use this much until second term though, but I want you to be aware when you show your arrows, be extra careful that you show it as a double arrowhead, because if you show it as a single barbed arrow like that, it means something entirely different. All right, so let's review a little bit. All right, so if we think about acid-base chemistry, we typically have some sort of base, and we've got some sort of acid that looks like this. Which one's going to be our electron source? The base, the lone pair on the base should be the source, and it's going to reach out and grab that proton. And what else do we need? The bond between the proton and our acid will be broken. So that covalent bond has two electrons, so we need to show this with the double-headed arrow, saying the two electrons in here, in fact, I'm going to go ahead and draw them like green dots, will end up on A. So now B will have a covalent bond to H, therefore B will have a positive charge. And then A over here will have two electrons kind of hanging off, and therefore it will have a negative charge. So we've actually seen this in context a handful of times. So let's make a few notes. Over here we had the electron source. Oh man, so you see, and then this is the destination. Be the proton right there. And then same thing here. If we think about this covalent bond, that was the source of electrons that ultimately gets delivered to A. So we have to be very careful about the directions in which we're showing arrows. Does that make sense? All right, so there's going to be a few new terms that I want to introduce today. And this will show up all year long. These are terms that won't go away. The first term is electrophile. All right. How many of you are familiar with Latin roots? A little bit? What does philia mean? Love. So in this case, electro-loving means electron-loving. Okay? Do you think this is going to be an electron source or electron destination? Destination, right? So we could say that this is electron-loving. Therefore, it's going to be our electron destination. And let's talk about nucleophiles down here. All right, same sort of root here, philia or phile in this case. That means loving. In this case, it's nucleo-loving, nucleus-loving. What property do nuclei have? Are they positive or negative? Positive. So in this case, a nucleophile is something that is positive loving. So in this case, it's typically going to have what? It must have some sort of electrons that can be given to that positive charge, right? So in this case, this is typically your electron source. So throughout the year, we'll be talking about this. Try to use that root system. So electrophile means electron loving, nucleophile means positive loving. So let's try to kind of narrow this down into more concrete examples. All right. So let's do nucleophiles over here, and I'll just abbreviate these NU, or actually I'll just write it out. And then say over here, in the future, I tend to abbreviate these as NU. And then electrophiles over here, I abbreviate as E+. All right. We said that nucleophiles are attracted to things with a positive charge. So typically they're the electron source. Another way of defining these is they're electron rich. Electrophiles, on the other hand, want electrons, so they must be opposite, right? So these would be electron poor. So let's take a look at a few of these. So in the first one, I've got this reagent right here. This is methyl lithium. All right. If we look at the carbon-lithium bond here, which element is more electronegative, carbon or lithium? Carbon, right? So if we look at this, we've got a net dipole, whoops, pointed towards the carbon, which means over here this lithium is partial positive. This carbon must be partial negative. So if we look at this carbon right here, this carbon is clearly electron rich, right? So we could point to this and we could say that this carbon is nucleophilic. All right, let's take another example over here. So kind of different. In this case, what's more electronegative, carbon or bromine? Bromine. So in this case, the dipole is going to be pointed in the opposite direction. So now we could say bromine has a partial negative. Carbon in this case will be positive. So if we look at this, we could say in this one that carbon is electrophilic. In this case, it's electron poor. Does that make sense? So in this case, it's really important that we understand the polarity of these molecules, because the direction of the polarity can impact whether or not carbon is behaving as a nucleophile or an electrophile. All right, let's do another one. My question for you is, let's analyze the oxygen here. Do you think the oxygen is going to be nucleophilic or electrophilic? Nucleophilic, why? Okay, so the net dipole, we said, is going up, so we can show it this way, which means that it not only has a partial negative versus the hydrogens, which are partial positive, but what else do you notice here? It has lone pairs, right? So if we look at this one, we can say that oxygen is nucleophilic and has lone pairs. In this case, the lone pairs could very much act as an electron source in this situation. All right, let's take another one. I'm going to draw it this way. This is BH3. What's the hybridization of boron here? So it's trigonal planar, right? It's flat. What would the hybridization be? SP, SP2, or SP3? Okay, so this would be SP2. Oops. We know all trigonal planar atoms are going to be SP2. So it must have this p orbital sticking up and down off of this. So if we think about it, will the boron be electron rich or electron poor? Electron poor, it has an empty orbital that could be a destination for electrons, right? So in this case, we could look at this and we could say empty p orbital wants electrons, therefore boron is electrophilic. All right, so that makes sense. Let's do a couple more. Let's say I've got this molecule over here. This is one of my favorite reagents. Which portion do you think is going to be the nucleophile? You think it's going to be the carbon, hydrogen, magnesium? What would be the nucleophilic atom here? Carbon, right? Carbon not only has a lone pair, but it even has a negative charge. So in this case, it's got a lone pair to donate. And a negative charge. All right, if we think about stability, are carbon atoms typically happy with the negative charge? No. So in this case, it really, really wants to get rid of those electrons to become more stable. So this is going to be an incredibly strong nucleophile. All right, let's take another example. I'm going to draw in all of my atoms. All right, so for this one, I'm going to actually slide everything down. On the right, what do you think the electrophilic atom would be? Carbon. In this case, it's got a positive charge, so this would be electrophilic. It wants electrons, right? All right, so in this case, we can see charge can also play a role in nucleophiles versus electrophiles. All right, there's one last one. It's a little harder to spot. But let's say we've got this molecule, cyclohexene, not cyclohexane, because it's got an alkene there. In this case, where do you think the nucleophilic site might be? What electrons could most easily be donated? The double bond, right? So in this case, one of the ones that students often forget about is pi bonds. All right, so if we look at these, here's a handful of examples that we went over. On the top, you see how we have partial charges. In the middle, as we go down, we've got neutral atoms, but we can kind of determine whether or not they have lone pairs or vacant p orbitals. On the bottom, kind of semi-bottom, we're looking at just full charges, so full negative versus full positive. And then the last but not least one for nucleophiles are the lone pairs. So we can kind of use these as a system for determining whether or not we're dealing with a nucleophile or electrophile. In general, when we're showing electron pushing arrows between our nucleophile and electrophile, which way should the arrows go? Should it go from the nucleophile to the electrophile or the electrophile to the nucleophile? The first one, right? We always want to show the electron source going to the electron destination because this is our electron-rich region. Does that make sense? All right, I know it's easy to mix those up though. All right, so let's do a little bit of practice. So I've got this molecule here. And when this reaction is all done, it's actually going to make a ring system. Boron will have a negative charge, and we'll have lithium over here with a positive charge. Let's identify where the nucleophilic site and electrophilic site is. So where do you think the nucleophilic site is on our starting material? So the nucleophilic site must be our electron-rich carbon atom. So what do you think? So let's think about boron. I hear a lot of people talking about boron. Does boron, in this case, want electrons, or does it want to give electrons? Wants electrons. So this must be our electrophile. Why does it want electrons again? Because of the empty p orbital, right? So empty p orbital means that this is our electrophile. All right, where would our nucleophile be then? Yeah, the carbon attached to the lithium. In fact, we said that there's a strong dipole here, right? So there's a strong dipole pulling electron density, so much so that in some cases, this bond can even be thought of as ionic, right? Because lithium's on the opposite side of the periodic table. We can even show this as an ionic bond. All right, so over here we can highlight this, and we can say that this could be our nucleophile. All right, so in this reaction arrow scheme, we go like this. Our nucleophile will attack our electrophile. And the other thing to consider, right, is we have 1, 2, 3, 4 carbons here, which makes sense because over here we've got 1, 2, 3, 4 carbons. So we're going to form that ring where boron is the 5th part of the ring system. Does that make sense? So in fact, we can number it all the way to 5 like that. So we can predict the reaction arrow pushing for this mechanism without even knowing much about it, right? So this will be a portion of your skill builders where they give you some complicated, scary looking reactions and you just have to stay calm, right? And then you have to ask yourself, all right, where's the electron source going to be? Where's the electron destination going to be? And then let's have arrow pushing connecting the two. All right, so I'll show you some common arrow pushing techniques. All right, first one's really easy. It's proton transfer. All right, and we've seen this quite a few times before, but that's when we have some sort of acid-base reaction. And we said that our base is going to reach out, grab our proton, and then we have to kick off electrons to A. You can show this with equilibrium arrows if you want, but that means that A would have a lone pair in the end, and then B will now have our covalent bond to our proton. So something we're hopefully pretty familiar with. Number 2 is what we just saw. It's our nucleophilic attack. Okay, so I'll show you a common example. Whoops. So we've got water. And I'll pick a World War I war gas, because why not? This is phosgene. All right, so the question is, which of these molecules do you think might act as the nucleophile? We've got a lot of lone pairs hanging around. Yeah, probably water, because it's got lone pairs and it's got strong partial negative. So in this case, this would be our nucleophile. So I'll just say Nu. So it's probably going to attack the other thing. In fact, when we go ahead and we look at our reaction intermediate over here, it kind of looks like this. Which makes sense, right? So in this case, oxygen has attacked the other molecule. All right, so in this arrow pushing sequence, water is going to act as the nucleophile. What do you think is going to be the electrophile based on looking at our products? The carbon, right? So over here, this must be our electrophile. Can anybody explain why this wants electrons? Why does that carbon want electrons so badly? It's 2 reasons. Yeah, 3 electronegative atoms are attached to it. That's one reason. What's another reason? Resonance structures. If we were to draw the second resonance structure, we could show that carbon with the positive charge, right? So in this case, that's a huge electrophile. So we can show electrons attacking that electrophilic carbon, but we can't have 5 bonds to a carbon, right? So just like with resonance, the solution to that is to break one of these bonds and kick it up to oxygen. Once we're done, we have to account for all of our formal charges, right? So in this case, oxygen that we kicked electrons up to would have 3 lone pair sets on it, giving it a negative charge, where the oxygen on water that attacked in would only have 1 lone pair, because the second lone pair formed a covalent bond. Therefore, that oxygen would have a positive charge. All right, so that's a common arrow pushing technique. And then number 3 is loss of a leaving group. And I call leaving groups just LGs because they're way too long to write out. And we actually saw this the other day in lecture, where iodine can actually just fall off of molecules. And when this happens, we can have a positive charge plus I with a negative charge. Does anybody know why this might happen? Why would iodine just fall off? It's heavy. What about this thing over here that I've highlighted? Is it very stable after it falls off? Yeah, absolutely. It's the conjugate base of a very, very strong acid. Iodine with a negative charge is actually quite stable. So when it falls off, it's happy falling off, right? So that's one way of thinking about it. So we will see this. What about the carbocation? Do you think this is very stable? No, the carbon with the positive charge is not stable. So it's kind of a mixed bag here. The carbon's less happy, but the iodine's reasonably happy. So we will see this occasionally as well. All right, and that takes me to my next one, which are rearrangements. All right, so let's do an example one. And in fact, I'm going to color code this just so we can keep track of everything. So this is our starting molecule. In this case, if we look at this carbon with the positive charge, is it a primary, secondary, or tertiary carbon? And how do we determine that? You remember how we did that when we were going through the alkane naming? What do we ask ourselves? We ask ourselves how many other carbons are attached to that carbon, right? So in this highlighted carbon, how many other carbons is it attached to? 2. So we would call this a secondary carbocation. What will happen is basically this entire hydrogen can just slide on over to that positive charge. So the hydrogen moved over with its electrons, right? So in this case, where would the positive charge be on our final product? It would be on the carbon on the far right. All right, if we look at the carbon on the far right, what sort of carbon is this one? Tertiary. This is normally the point where students look at me and they're like, why are atoms just moving around like this? This doesn't make any sense. And that's where we have to kind of pause for right now. We have to understand why. Why would we prefer to go from a secondary carbocation to a tertiary carbocation? So let's take a pause. All right, are carbocations stable? What do you think? No. Okay, so carbocations are unstable. Why are they unstable though? They're a positive charge. Carbon would prefer to be neutral if possible, right? And carbon, yeah, it's not very electronegative, but it still doesn't want a positive charge. So in this case, carbocations are unstable, but various features can help. All right, what's one feature that could help stabilize a positive charge that we've seen a lot of? Resonance. This helps a lot. Why does resonance help a lot if you have a positive charge? Spreads it out, right? So you're not forcing the positive charge to live on any one specific atom. You can move it around using resonance, right? So that's really helpful. The second one is one we haven't seen. This helps a little. All right, so let's talk about hyperconjugation. All right, so I'm going to draw out an example molecule over here. And I'm just going to use R groups over here just to keep things relatively simple. If we think about this carbocation right here, what's the hybridization for it? Must be sp2, right? What about this carbon over here? sp3. All right, so let's try to draw this a little bit differently. So what I'm going to do is still stick with these R groups. We want to remember that they're there. But we know that the middle carbon, being sp2, must have a p orbital coming off of it, right? Let me clean this up. So this would be an empty p orbital. All right, the carbon on the far right, or sorry, far left-hand side, does it have a p orbital? No. If we were dealing with resonance, it would have a p orbital, right? But in this case, we can clearly see that it's sp3 hybridized and there's no resonance going on here. All right, so what I'm going to do is I'm going to show one of those sp3 lobes. All right, so this sp3 lobe we know is going to be kind of like a tetrahedral clover. I'm going to show our remaining two hydrogens just kind of plain. But out here, I'll show this third hydrogen like this. Does that kind of make sense? So I'm just choosing to show only one of our three sp3 lobes coming off of that carbon. Are there any questions at this point? I know it's some review. All right, so when an sp3 lobe is in close proximity to an empty p orbital, you actually get weak overlapping interaction. So weak stabilizing interaction. So what does this tell us? It tells us a few things. First thing is carbocations are stabilized by neighboring sp3 hybridized carbons, because we get more of these interactions. All right, so let's kind of try to make some claims here. Oops. So we know that stability can be measured. Resonance is the best. If we think about carbocations that don't have resonance, would it be better to be a tertiary carbocation, secondary, or primary carbocation? Tertiary, why? Yeah, exactly. If we have a tertiary carbocation, we've got three sp3 hybridized carbons around it, right? So we get three of these stabilizing interactions from hyperconjugation. So resonance is more stabilizing than tertiary carbocations, which is more stable than secondary, which is more stable than a primary carbocation, which is way more stable than a CH3 carbocation, right? So over here, we've got more stable. This is least stable. Does that make sense? So it's similar to resonance where you get the stabilizing interaction, but you're not actually spreading the charge around. You're just getting a weak stabilizing interaction from a neighboring sp3 orbital. All right, so I know it's a little bit tricky. So let's go back into examples of rearrangements. Sorry, let me make sure I'm not skipping anything in my notes. I thought I had more examples than this, but we'll stick with these. All right. We'll do this one over here. And I'm going to stick with basic bond line structures. I'm going to say, all right, right here, is this a primary, secondary, or tertiary carbocation? Okay, so this would be a secondary carbocation. All right, secondary carbocations, it's reasonably stable, right? It's got two of the stabilizing interactions. Could it be better? Yeah. All right, it could be a tertiary carbocation, which would be much better. Is there any way we could get resonance in this molecule, though? No. So the best case scenario is maybe we could convert this from a secondary carbocation to tertiary. So what we could do is we could look at the neighboring carbons. So we could say, all right, there's two neighboring carbons right there. The carbon on the right has 3 hydrogens. And just to really make things clear, I'm going to draw in the hydrogen right there in black. Does that make sense? So I haven't really changed anything. What we could say is, well, what if we did a rearrangement where we took this hydrogen and we just slid it over next door to that carbocation? Oops. Let me keep it all color-coded. Shoot. Then we would have a positive charge here, and that blue proton would have shifted over. What sort of carbocation did we form? This would be a primary carbocation. Is this very favorable? No. So we're going to less stable. This will not happen. The reaction is non-spontaneous. Meaning it'll favor the starting materials, right? This reaction won't proceed in a friendly way. All right, so this kind of presents a problem though, right? Because we know secondary carbocations aren't super stable. All right, what could we do differently, do you think? Anybody have an idea? So you're saying instead of moving the hydrogen on the right, what if we moved one of the other groups over? I think that's a really good idea. So let's try that down below. So I'm going to redraw the exact same reaction. Down here. And in this situation, you're saying, let's move one of these CH3 groups over. In fact, I'm just going to label all of these CH3s. So we could take this entire group right here. We could shift this entire group over. Oh man, my drawings are not very good today. I apologize. So over here, you see how this CH3 group kind of slid over? What am I missing though? My positive charge. Where should the positive charge be? On the left carbon. Okay, so I'll put that in. So over on the left-hand side, we already said that this is a secondary carbocation. What about on the right-hand side? It'd be tertiary. All right, so in this case, going from secondary to tertiary, we're making the system more stable. Therefore, the reaction is spontaneous. All right, there's a couple things you really have to pay attention to with these. You notice how in the top example, I moved a hydrogen that was next door to the carbocation. And in the bottom example, I moved a methyl group that was next door to the carbocation. We can only move next door atoms or groups. So let's make a note of that. All right. So let's go through and kind of describe these in more detail. So in the example shown above, you see how we moved a methyl group over? This can be called one of two different things. This can be called a 1,2 methyl shift. What do you think the 1,2 stands for? Yeah, essentially it's saying it's carbon 1 to carbon 2, meaning they're next door neighbors. 1,3 would be one atom removed even further away. So it doesn't have to do with IUPAC numbering, it's just relative positioning, saying that they're next door neighbors. So this is often referred to as a 1,2 methyl shift. Or what if we didn't move a methyl group? What if we moved some other big chain? Sometimes this is referred to as simply a 1,2 alkyl shift. Both of them are the same. It just means that some sort of hydrocarbon moved. Maybe not a methyl group, maybe it was something else. In this case, it was a methyl group. All right, let's go up more though. We'll go back to our original one. In this rearrangement, you see how we moved that orange hydrogen? Did we move a proton, a hydrogen, or did we move something else? What do you think? Let's make some notes here. In fact, I'll do it in the top. If we think about hydrogen, hydrogen has one electron. If we have H+, that's a proton. In this case, we moved a hydrogen and both of its electrons with it. So we can't call it hydrogen, we can't call it a proton. Does anybody know what it's called when you have hydrogen with 2 electrons with it? In this case, it would actually be negative if it's by itself. This would be hydride. So in this case, this is referred to as a 1,2 hydride shift. So anytime you move a hydrogen with its electrons over, we call it a hydride shift because we don't want to confuse that with protons and normal hydrogens. Does that make sense? Okay. So students get confused and they say, well, when do we know when a rearrangement will occur? Does anybody have an idea? Well, if we went down to these examples, we said in the first case, the reaction will be non-spontaneous. That gives us a clue that it wouldn't occur, right? We know non-spontaneous reactions just don't occur because it's going to a less stable carbocation. On the bottom example, we said that this reaction is spontaneous because we're going to a more stable carbocation, so this would occur. So assume rearrangements will occur if you can form a more stable carbocation. Does that make sense? All right, so that's really where we're going to end off today. I apologize that we didn't have enough time to get into our in-class activity, but let's take a look. The in-class activity is already giving you the starting materials and products, and it just wants you to fill in the arrows that are missing for part A through D. And then E is a challenge problem. E is meant to be a challenge problem. I will not put a problem like E on the exam, but if you're up for a challenge, see if you can figure out how to get from these starting materials to these products. And what do the 4 arrows mean? It might take 4 or more steps. So in this case, it's going to be more than 1 step. See if you can figure out how to get from the starting materials to the products using proper arrow pushing. It may involve a variety of different arrow pushing techniques. All right, I hope that helps. Let me know if you have any questions. I'll be available via email this weekend.